Imagine pointing the most powerful telescope ever built at a patch of sky and seeing almost nothing. No spiral arms, no glowing core, no river of stars. Just 4 faint points of light huddled together in the dark, 300 million light-years away. That's CDG2. And what makes it extraordinary isn't what you can see, it's what you can't. On February 18, 2026, NASA announced that the Hubble Space Telescope, working alongside ESA's Euclid Observatory and the Subaru telescope in Hawaii, had confirmed the existence of a galaxy that is 99% dark matter. Not 50%, not 80, 99. You clicked because a galaxy made almost entirely of invisible matter sounds like it shouldn't be real. By the end of this video, you'll understand why the real shock isn't that CDG2 exists. It's that we almost certainly missed hundreds more just like it, hiding in plain sight across the observable universe. But before we get there, we need to start with a question that changes how you think about galaxies entirely. What if the stars are the exception, not the rule? When most people picture a galaxy, they picture light. The Milky Way's grand spiral, Andromeda's glowing disk. Billions of stars packed together, forging elements, blasting radiation, illuminating the void. And that picture isn't wrong, it's just incomplete. Because every galaxy we've ever studied sits inside something much larger and far heavier than the stars themselves. A halo of dark matter. Dark matter doesn't glow, it doesn't absorb light, and it doesn't bounce off anything we can build a detector for, at least not yet. But it pulls, it warps space-time, and without it, galaxies as we know them couldn't hold themselves together. The stars would drift apart like sparks from a dying fire. In our own Milky Way, dark matter outweighs ordinary matter by a factor of roughly 6 to 1. That's already strange. But CDG2 takes the ratio to a completely different place. 99% of CDG2's total mass is dark matter. Its visible output, all the starlight it produces, is equivalent to about 6 million suns. That sounds like a lot, until you remember the Milky Way pumps out the light of tens of billions of suns. CDG2 is radiating less than 1/1000th of what our galaxy does. It contains just 4 globular clusters. 4. The Milky Way has over 150. And those 4 clusters account for roughly 16% of all the light CDG2 produces. So if you could somehow remove those 4 ancient star clusters, this galaxy would drop even further into the dark, approaching something almost undetectable. Here's the part that stops you in your tracks. How do you find a galaxy that barely shines? The answer is, you don't look for starlight at all. You look for breadcrumbs. Traditionally, astronomers find galaxies the same way you'd spot a campfire in a dark forest. You look for the glow. You scan the sky for patches of concentrated light, and when the math says those photons belong together, you've got a galaxy. But what if the campfire has gone out, and all that's left are a few embers? That's the insight David Lee, a postdoctoral researcher in statistics and astrophysics at the University of Toronto, brought to the problem. Instead of looking for diffuse starlight, Lee's team searched for something much smaller and much tougher: globular clusters. Globular clusters are ancient, dense balls of stars, sometimes hundreds of thousands of them, packed into a volume just a few dozen light-years across. They orbit most galaxies like tiny satellites, and crucially, they're extremely resistant to being torn apart. Even in the most violent gravitational environments, globular clusters tend to survive. So Lee asked a simple but powerful question. What if we scan the sky not for galaxy-sized patches of light, but for statistically unusual groupings of globular clusters that don't seem to belong to any known galaxy. Think of it this way. You walk into a completely dark house. You can't see the walls, the furniture, the floor. But you notice 4 small nightlights plugged into the walls, clustered closer together than random chance would predict. You don't need to see the house to know it's there. That's exactly what happened. Lee's statistical technique combed through deep imaging data and flagged tight groupings of globular clusters. Out of that search, 10 previously known low-surface brightness galaxies were recovered, a good sign the method works. But 2 additional candidates popped up that had never been identified before: CDG1 and CDG2. CDG2 was the stronger signal. 4 globular clusters, sitting suspiciously close together in the direction of the Perseus Galaxy Cluster, roughly 300 million light-years away. No obvious galaxy connecting them, and just 4 ancient star balls hanging in space, as if orbiting a ghost. Now, you might be wondering, 4 clusters doesn't sound like much to go on. Couldn't that just be a coincidence? 4 unrelated clusters that happen to sit near each other? Lee's team ran the numbers on exactly that question. They calculated the probability that 4 globular clusters would land this close together by random chance, given the average density of clusters across the Perseus field. The answer: vanishingly small. The clustering was statistically significant enough to demand follow-up. And here's what's subtle about this approach. Lee didn't just find CDG2 by eyeballing an image. He built a statistical pipeline that could be applied to any deep imaging survey. That means this isn't a one-off trick. It's a reusable method and a template for hunting invisible galaxies at scale. But a statistical signal isn't proof. To confirm there was actually a galaxy hiding behind those clusters, the team needed eyes. Multiple sets of very expensive, very precise eyes. Cosmic tide viewers know to ask a practical question here. What did the telescopes actually measure? Let's walk through it. The first instrument brought to bear was the one that started it all: the Hubble Space Telescope. Using its advanced camera for surveys, Hubble delivered the sharpest images of CDG2's 4 globular clusters. At Hubble's resolution, the team could measure the precise positions and brightnesses of each cluster and confirm they were genuinely located at the distance of the Perseus Cluster, not random foreground objects that happened to line up. But Hubble alone couldn't settle the question. Seeing 4 clusters is one thing. Proving there's a galaxy underneath is another. Enter Euclid. ESA's Euclid Space Observatory, which launched in 2023, was designed to map the large-scale structure of the universe. It wasn't built specifically to find dark galaxies, but it has a superpower that turned out to be perfect for this job. Wide-field, ultra-deep imaging across optical and near-infrared wavelengths. When Francine Marlot at the University of Innsbruck examined Euclid's images of the Perseus Cluster, something appeared. Around CDG2's 4 globular clusters, Euclid detected a faint, diffuse glow, an extremely low surface brightness haze of starlight that was too dim for most surveys to catch. This wasn't noise, and the shape and position of the glow matched across independent Euclid filters. Now the team had Hubble confirming the clusters and Euclid revealing the ghost glow. But one more check was needed. Could the diffuse emission be an artifact, some stray light, a processing glitch, an optical ghost from a nearby bright galaxy? To rule that out, they turned to the Subaru telescope on Mauna Kea, Hawaii. Subaru's hypersuprime cam is one of the most sensitive ground-based wide-field images in the world. When the Subaru data lined up with Euclid's, showing the same faint emission in the same spot, the case closed. 3 independent telescopes, 3 different instruments, 3 different teams analyzing the data. All of them agreed there is a galaxy at that location, and it is extraordinarily faint. If you only saw the headline, "Galaxy made of 99% dark matter," you might think this was a single dramatic observation. The actual story is quieter and more convincing. It's a statistical detection, confirmed by 3 of the most powerful observatories humanity has ever built, each covering a different piece of the evidence. But confirming CDG2 exists is only half the puzzle. The deeper question is, why is it like this? Why would a galaxy lose almost everything except dark matter? To answer that, we need to zoom out, way out, and look at where CDG2 lives. The Perseus Cluster is one of the most massive galaxy clusters in the nearby universe. It contains thousands of galaxies, all bound together by gravity, swimming through a sea of superhot gas that radiates in X-rays. The central galaxy, NGC 1275, this is an active monster pouring jets of energy into the surrounding medium. Galaxy clusters are beautiful, but they are not gentle places. When a smaller galaxy falls into a cluster like Perseus, it doesn't just glide in peacefully. It slams through the intra-cluster medium, that hot gas filling the space between galaxies, at speeds that can exceed 1,000 kilometers per second. What happens next is called ram pressure stripping. Imagine driving a convertible through a rainstorm at 200 miles an hour, except you're not getting wet. You're getting your atmosphere ripped off. The intracluster gas hits the infalling galaxy like a cosmic headwind and pushes out its cold hydrogen gas, the raw fuel for star formation. No gas, no new stars. And over billions of years, the old stars fade and die, and nothing replaces them. But here's where CDG2 interesting interesting. Ram pressure stripping removes gas, the lightest, most loosely bound material. Dark matter, by contrast, doesn't interact with gas at all. It only responds to gravity. So while the gas gets blown away, the dark matter halo stays put. Now picture a galaxy that was probably modest to begin with, maybe a low-mass dwarf, falling into the Perseus Cluster billions of years ago. The cluster's gravitational tides and ram pressure winds stripped away its gas. Star formation shut down. Over cosmic time, the few stars it had dimmed and aged. What was left was a skeleton, a dark matter halo with almost nothing inside it that can produce light. That's CDG2, a dark matter skeleton with 4 stubborn globular clusters still clinging to it. And those globular clusters survived because they are extraordinarily dense. Gravitational tides that would shred a diffuse star-forming cloud barely dent a globular cluster. They are the toughest stellar structures in the universe. So when everything else was stripped away, the clusters endured. The last visible trace of a galaxy that lost nearly everything else. And CDG2 may not be alone in this. The Perseus Cluster is home to thousands of galaxies, and the conditions that created CDG2, intense ram pressure stripping, repeated gravitational encounters, have been operating for billions of years. If one galaxy was reduced to a dark matter skeleton, it stands to reason that others in the same environment could have suffered the same fate. We just haven't looked for them the right way until now. And there's also the tantalizing detail of CDG1, the other candidate that Lee's statistical search turned up. CDG1 is even more extreme than CDG2. No diffuse emission was detected around its globular cluster grouping at all. If CDG2 is a ghost, CDG1 might be a ghost's ghost. A galaxy so thoroughly stripped that even its faintest starlight is gone. The team hasn't confirmed CDG1 yet, but its existence at the edge of detectability hints at a whole spectrum of dark galaxies, grading from barely visible to truly invisible. But the story doesn't stop at stripping. because CDG2 raises a much bigger question about galaxies and dark matter, one that flips a famous discovery on its head. Remember that odd spike we mentioned earlier? The idea that some galaxies seem to exist at the extreme edges of the dark matter spectrum. And CDG2 isn't the first time astronomers have found a galaxy that challenges the standard ratio. In 2018, a team led by Peter van Dokkum at Yale announced something that sent shockwaves through astrophysics. A galaxy called NGC 1052-D F2 that appeared to contain almost no dark matter at all. Its globular clusters were moving so slowly that the galaxy's total mass could be explained by its stars alone, with no room left for an invisible component. That was deeply weird. Standard cosmology says every galaxy should sit inside a dark matter halo. Dark matter is supposed to be the scaffolding on which galaxies are built. A galaxy without dark matter is like a building with no foundation. And then Van Dokkum's team found a second one, DF4, with the same property. Two galaxies, nearly devoid of dark matter, in the same galactic neighborhood. And now look at what CDG2 tells us. Nature apparently makes galaxies at both extremes. Galaxies with almost no dark matter, and galaxies that are almost nothing but dark matter. That's a powerful clue. If dark matter were simply an artifact of our gravity equations being wrong, as some alternative theories like MOND suggest, then you wouldn't expect to find galaxies where dark matter and normal matter have been cleanly separated. Modified gravity predicts that what we call dark matter effects should always track where normal matter is. But CDG2 and DF2 together show that the invisible mass and the visible mass can exist independently of each other. One galaxy kept its dark matter and lost its stars. Another kept its stars and lost its dark matter. That's hard to explain without dark matter being a real and physical substance, something that can be gravitationally stripped or retained depending on environment. Now, we should be careful here. The Dragonfly 44 saga is a cautionary tale. In 2016, Van Dokkum's team announced a galaxy in the Coma cluster that appeared to be 99.99% dark matter, even more extreme than CDG2. That claim made headlines worldwide. But subsequent studies revised the numbers downwards significantly. A 2020 reanalysis found that Dragonfly 44's globular cluster count had been overestimated, and its dark matter content was likely much more ordinary. Cosmic Tide viewers know to ask the follow-up. Could CDG2's numbers be similarly revised? It's possible. The paper itself notes uncertainties in the globular cluster luminosity function and in the faint diffuse emission measurements. But unlike Dragonfly 44, and CDG2 has triple telescope confirmation of both its clusters and its diffuse glow. The statistical grounding is stronger. Still, in science, one paper is a beginning, not a verdict. What matters most right now isn't whether CDG2 is exactly 99% dark matter, or 97%, or 95%. What matters is that a galaxy this dark was found at all, and the method used to find it could open a floodgate. Here's the question that keeps astronomers awake. If CDG2 was this hard to find, how many more are out there? Traditional galaxy surveys are fundamentally biased toward light. We count what shines. If a galaxy doesn't produce enough photons to rise above the background noise of the sky, it might as well not exist, at least from our perspective. Lee's globular cluster method sidesteps that bias. Instead of looking for a faint galaxy and then finding its clusters, you find the clusters first, and then check whether they trace a galaxy. It's detection in reverse. and it could work across any deep imaging survey. 3 upcoming missions could transform this into a census. Euclid is already surveying a third of the sky at depths that can detect ultra-faint structures. NASA's Nancy Grace Roman Space Telescope, set to launch in the coming years, will deliver Hubble-quality resolution over fields 100 times wider. And the Vera C. Rubin Observatory in Chile will begin its decade-long survey of the southern sky, generating an unprecedented catalogue of faint objects. If machine learning and statistical methods like Lee's are applied to these datasets, the number of known dark matter-dominated galaxies could jump from a handful to hundreds, maybe thousands. And every one of those discoveries reshapes the denominator in our cosmic census, the total number of galaxies in the universe, in a direction we hadn't anticipated. Think about what that means for our models. When we calculate the total matter density of the universe, we rely on galaxy surveys. We count galaxies, estimate their masses, and add them up. But if a significant population of galaxies is too dark to appear in those surveys, our census has a blind spot. The matter is there. The gravitational effects are real. But the galaxies themselves are ghosts in the data. This also matters for something called the missing baryon problem. Cosmologists know how much ordinary matter the universe should contain, and based on the cosmic microwave background. But when they add up all the ordinary matter they can actually find in stars, gas, dust, the hot plasma between galaxies, the total falls short. Some of those missing baryons might have been inside galaxies like CDG2 once, before they were stripped away and dispersed into the intergalactic medium. Dark galaxies could be part of the chain that explains where the universe's missing normal matter went. We think of the universe as a sea of luminous galaxies. But what if the sea is full of invisible ones too? Dark matter halos with almost no starlight, floating between the bright islands we can see. CDG2 suggests that the cosmic web may be far more populated than our light-based surveys have ever told us. So let's pull the threads together. CDG2 is a galaxy in the Perseus Cluster, a roughly 300 million light-years from Earth. It produces the light of about 6 million suns, less than 1,000th of the Milky Way's output. It contains just 4 globular clusters, which account for roughly 16% of all its visible light. And preliminary analysis suggests that 99% of its mass is dark matter. It was detected not by its starlight, but by a statistical method that searched for unusual groupings of globular clusters, the first galaxy ever found this way. 3 major telescopes confirmed it independently. Its extreme dark matter fraction is likely the result of environmental stripping inside one of the most violent galactic neighborhoods in the nearby universe. It probably started as a modest dwarf galaxy, fell into the Perseus Cluster, and had its gas torn away by ram pressure forces, by shutting down star formation and leaving behind a dark matter halo with almost nothing luminous inside. Together with galaxies like DF2, which appear to lack dark matter entirely, CDG2 suggests that dark matter and normal matter can be separated, a finding that supports the existence of dark matter as a real substance, not merely a quirk of gravitational math. And there's something quietly profound in the method itself. For most of the history of astronomy, we've explored the universe by chasing light. Brighter meant more important. Luminosity was the currency of discovery. CDG2 is a reminder that some of the most massive structures in the cosmos produce almost no light at all. The universe has been hiding things from us, not behind walls, but in plain sight, below the threshold of what we thought to look for. And the universe is stranger than headlines can capture. A galaxy made of 99% invisible matter found by 4 tiny points of light in a cosmic crowd of thousands. We didn't see it because we weren't looking the right way. And the fact that a statistician working with a 35-year-old space telescope and a brand new European observatory could reveal something this hidden, that's its own quiet kind of miracle. The question now isn't whether more ghost galaxies are out there. It's how many we've been walking past in the dark.